Welcome to The Explainer. Today, we're diving straight into the incredibly efficient heart of modern computing, the five-stage MIPS pipeline. If you've ever wondered how your devices process billions of calculations per second without completely breaking a sweat, well, you're in the exact right place.
So let's tackle this head-on. How does your computer seemingly do everything at once without bottlenecking or freezing up? We're going to look under the hood today to see how a deceptively simple structural philosophy completely transformed processor speed. Here's our roadmap for this explainer. We'll quickly cover the sequential problem, the pipelining solution, the 5 specific MIPS stages, do a deep dive into the data path, see pipelining in action, and wrap up with handling hazards. Let's get right into it.
Starting with Section 1, the sequential problem. Let's look at what actually happens when a processor tries to do things the old-fashioned sequential way.
To really appreciate pipelining, we kind of have to grasp the multiple cycle implementation first. In a multiple cycle setup, the processor literally waits for one instruction to completely finish all of its operations before it even thinks about starting the next one. Think about doing laundry, right? If you wait for the washer and the dryer to completely finish one load before starting your next basket of dirty clothes, you're wasting hours of time. But if you overlap them, putting a new load in the washer while the first load is tumbling in the dryer, you save massive amounts of time. That overlapping, that is the absolute core philosophy of pipelining.
Moving to Section 2, the pipelining solution. Computer architects essentially took that brilliant laundry overlapping analogy and applied it directly to microscopic hardware on a silicon chip.
The crucial takeaway here is that every single MIPS instruction is broken down into 5 exact, distinct stages of a metaphorical assembly line. Those stages are instruction fetch, decode, execute, memory, and write back. By strictly defining these 5 steps, the processor can just hand off an instruction from one stage to the next, which instantly frees up the previous stage to accept a brand new instruction. It's a real game changer.
Section 3, the data path deep dive. Let's break down the specific jobs happening at each of these 5 hardware stations.
First up is instruction fetch, or IF. In this very first stage, the processor simply fetches the command it needs to perform from the instruction memory. But simultaneously, it takes the program counter, which is basically the tracker of where we are in our code, and adds 4 to it. It adds 4 because instructions are 32 bits, or 4 bytes long. So this instantly queues up the internal counter to point to the next task in line.
Picturing this exact logic flow, starting with the fetch step at the very top, the instruction being pulled from memory happens in perfect lockstep with the program counter updating itself. It's perfectly synced.
Once fetched, the processor passes the instruction to Stage 2, which is decode. Here, the processor analyzes the instruction to figure out exactly what it's being asked to do. It breaks those 32 bits apart to find the exact source and destination registers, known as RST and RD, needed to actually pull the operation off.
Then we hit Stage 3. This is where the actual math or logic happens, inside the arithmetic logic unit, or ALU. If it's a math operation, it processes the data right here. But if it's a memory instruction or a branch, the ALU's calculating power is instead used to figure out exactly where to look in memory or exactly where to jump next in the program.
Now, depending on whether it's an R-type math operation, a load, a store, or a branch instruction, the execute stage kind of acts like a dispatcher. It routes the data down very specific hardware paths to ensure the correct mathematical result or memory address is generated for the very next step.
In the 4th stage, memory, we're dealing with external data. If the instruction needs to pull data from the main data memory to be used later, which is a load, or save a computed value into memory, which is a store, well, it happens right here, using that precise address we calculated back in Stage 3.
Finally, in the 5th stage, the operation is completed by writing the result securely back into the processor's register file. This write-back stage updates the system state. That means the fresh data we just calculated or loaded is now ready and waiting in the register, ready to be used by any future instruction coming down the pipeline.
Because these 5 independent hardware units each have their own dedicated physical space on the chip, meaning the instruction memory, the ALU, and the data memory are physically separate components, they can absolutely handle different instructions simultaneously. No waiting required.
Section 4, pipelining in action. So now that we know the 5 stations fetch, decode, execute, memory, and write back, let's look at the aha moment where they all actually work together at the exact same time.
When comparing multiple cycle to pipeline execution, it's wild how much time sequential processing wastes.
The pipeline implementation elegantly overlaps the fetch, decode, and execute stages. By the 5th clock cycle, you literally have 5 different instructions executing in 5 different stages at the exact same time. This constant overlap slashes total processing time and absolutely maximizes throughput.
Section 5. Handling pipeline hazards. Of course, overlapping instructions can create traffic jams, which are known in computer science as hazards. If 2 instructions try to use the same piece of hardware at the same time, the whole pipeline could crash.
To prevent structural hazards or physical clashes, the pipeline design strictly requires each functional unit to be used only once per instruction. But, what happens when an old instruction is trying to write back to the register file, while a brand new instruction is trying to decode and read from that same register file? To solve this, architects physically separated the read and write ports on the register file. Think of it like adding a separate door to the back of your laundry machine. One person can put dirty clothes in the front, while someone else pulls clean clothes out the back at the exact same moment. It prevents a clash entirely. Pretty clever, right? This leaves us with a really fascinating final thought. If this elegant, in-order 5-stage pipeline revolutionized computing by allowing instructions to overlap safely, how do today's superscalar processors bend these rules to execute even faster? How do they predict branches and execute out of order to push past these fundamental limits? Well, we'll leave that for you to ponder until our next explainer.